So today, what we're going to do is we're going to talk about what are called local sets for the Gaussian free field. And throughout, I'm going to be assuming that H is a Gaussian free field on D. And for simplicity, it's going to be helpful to assume that D is bounded and also simply connected. So everything that I'm going to say is not going to depend too strongly on the fact that D is simply connected. It just makes some of the statements a little bit nicer. And before I get started in local sets, I first need to remind you a couple of things about the circle average process. So remember, we wrote h sub epsilon of z for the average of our Gaussian free field on the boundary of the ball centered at z of radius epsilon. So that was our notation for that. And we did a calculation before that said that, well, first of all, let me also remind you that the map, which associates an epsilon z pair with its corresponding circle average, we showed that this is a continuous Gaussian process. And we did this calculation that said that the covariance function for this process, so the covariance of the average about the circle of radius epsilon 1 centered at z1 with the average of the field, the circle centered at z2 of radius epsilon 2, is just given by taking the Green's function for the Laplacian on our domain and integrating it against the uniform measures supported on these two circles. So here this is this was the Green's function on our domain, and these two things, these are the uniform measures on the boundary of boundaries of our two circles. Okay, so this is something that we derived earlier. And when we did this calculation, along the way, we showed that we can write h sub epsilon of z. This is the same thing as the inner product of h with this function psi sub epsilon of z, where this function psi epsilon of z, this is given by the minus 2 pi times the inverse Laplacian of rho sub epsilon of z. And this function has an explicit formula. Remember, it's just given by minus the log of the maximum of epsilon and the distance between z and y, minus another function, which we call g tilde z comma epsilon of y, where this function here, this is just the harmonic extension of the function which associates with a given y minus the log of the maximum of epsilon and the distance between z and y. Okay, so here you think of z being fixed, and this function here is given by the harmonic extension of this thing from the boundary of our domain to the interior of the domain. Okay. And yeah, and so when we derived this formula here for the covariance function of the circle average process, along the way we used that we used this representation of the circle average here, and what you can get is that the variance of h epsilon of z, This is explicitly given by just given by the norm of psi epsilon of z squared. Okay. All right. Now, right. Okay. So now, if our point z here, if this point has distance at least epsilon from the boundary, of the domain, then what is this function g tilde? So g tilde z sub epsilon at z, this is going to be equal to the harmonic extension of the map, which of the map y goes to minus the log of just the distance between z and y from the boundary of the domain to the interior evaluated at z. Okay, and the reason for this, of course, is that if your point is far enough away from the boundary, then when you take the maximum in the definition of g tilde up there, the epsilon term is never going to appear, and so you're just going to get this for g tilde at z. And if you remember from earlier, this function had a name. This is what we called just g hat sub z at z, because there's no epsilon dependence anymore. And one thing that I told you earlier is that this can be expressed in another way. It turns out that this here is equal to the minus log of what's called the conformal radius of z in d. Okay, so here let me remind you of what this is. So the conformal radius of z in d, which I'm going to write using this notation. So the conformal radius of z in d, this is equal to phi prime of 0, where here phi is the unique conformal map which goes from the unit disk to d with phi of 0 equal to z and phi prime of 0 positive. Okay. So if you haven't seen this fact before, that you can represent the conformal radius in this particular way in terms of this function, this is actually a very nice complex analysis exercise to check this. Okay. And yeah, so what do we get in the end? So what we get is that the h epsilon of z, this is a normal random variable. So this is a Gaussian random variable with mean 0 and variance given by minus log epsilon plus the log of the conformal radius of z in D. Okay? And so we're going to use this, this fact about circle averages in just a little bit when we look at one particular important property of local sets. All right, so now before jumping right into local sets, let me remind you of the Markov property for the Gaussian free field one more time. So what the Markov property says is that if U in D is open, then we have that we can write the Gaussian free field H as a sum H1 plus H2, where this H1 here is harmonic in U, and H2 is a Gaussian free field in U. Okay, and moreover, these two fields, H1 and H2, are independent. All right, and so these local sets that we're now going to look at, these are going to somehow are going to generalize this to the setting in which U is random. So they generalize the Markov property to random subsets in D. Okay. All right, so let me just introduce a little bit more notation now. So I'm going to let gamma, this is going to be the set of all closed sets in the closure of D. And I'm going to equip this with the Hausdorff metric. So and let me just remind you that that the Hausdorff distance for sets S1 and S2, which are both in gamma, is just given by the smallest epsilon positive, such that S1 is contained in the epsilon neighborhood of S2 and vice versa. So, okay, so this is the, using this notation here for the epsilon neighborhood of SI for I equal to 1, 2. Okay, so that's our space, and okay, so now let's suppose that we have a random variable A and this is coupled with our Gaussian free field H. Okay. Then we say that this A is local for H. If it's true that we can produce a sample of H using the following steps. Okay, so the first thing that you do is you sample a pair A comma H sub 1, where here H1 is it's a distribution which is harmonic in the complement of A. Okay, so that's the first thing that you do. And once you've picked your pair AH1, the second thing that you do is, given this, you sample a Gaussian free field in the complement of D, sorry, in the complement of A. And this Gaussian free field I'm going to call H2. Okay, and then you set H equal to H1 plus H2. Okay, so a set is a local set for the Gaussian free field if there's a way of sampling from the law of the free field such that you first pick a distribution which is harmonic in the complement of A, and then once you've picked your distribution, you can sample an ordinary Gaussian free field in the complement of A, and then take the sum of these two objects. Okay, so this is this is exactly analogous to the Markov property for the Gaussian free field, except this set A here is allowed to be a random set. No. So this is it's a random variable which takes values in the space of distributions, which is harmonic in the complement of A. And right, and so that's all that I'm saying about this particular part here. So one thing that I want to emphasize is that A does not have to have any interior. So you could imagine, for example, that if this is your domain, you could have just a line, and that would be an example of a local set. Right.
So you want to obtain the distribution of only H, or you want to obtain simultaneous distribution of A and H as in your coupling?
Right. So this would okay. So I'm sampling both A and H together. This is the procedure.
I'm slightly confused. What object is A? Is it a random set or?
A is a random variable which takes values in the space of closed sets. So it's a random closed set. Okay, does anybody have any other questions about the definition of a local set? Okay. All right, so okay, so this is what the definition is. This idea of local sets, this was first introduced by Schramm and Sheffield. And this was first in their paper called the contour lines of the continuum Gaussian free field. Okay, so they have a section about local sets in this article, and let me also mention that there's a very nice section about local sets in the lecture notes that Wendelin has written on the Gaussian free field, which you can also find on his website. So here are some examples of local sets. So first of all, if you just have a deterministic closed subset of your domain, then the Markov property tells you that this is going to be a local set. Okay, so that's kind of the simplest example. Another example in which the set is random is one of these SLE curves coupled with the Gaussian free field as a flow line, level line, or counterflow line, depending on the value of kappa. This will give you a random set which is local for the Gaussian free field. All right. And how should you think of local sets? So local sets you can kind of think of as arising by kind of exploring the values of the Gaussian free field in sort of a Markovian way. Okay. So these often come up when you sort of probe the values of the Gaussian free field using some kind of algorithm which is somehow Markovian. Okay. So for example, in the case of flow lines of the Gaussian free field, in order to generate a flow line, you just need to sort of observe the values of the field on top of the flow line, but you don't need to see anything else. And so this is an example of this type of local set. And you can think of this as somehow being kind of like the strong Markov property, something like the strong Markov property for the Gaussian free field. And yeah, and so this theory is actually extremely useful when you're working with the SLE Gaussian free field coupling. In particular, not every local set arises this way. There are some very important examples, which I unfortunately don't have time to talk about, which cannot be generated with an algorithm like this. So not every local set can be generated using an algorithm. Okay. Now, in their article, this article by Schramm and Sheffield, they have this this section on local sets, and they sort of develop the basic theory of them. And the types of results that they prove are number one, they have a bunch of different methods for determining whether or not something is local. And this is actually contained in just one lemma in their paper, but this turns out to be extremely powerful when you work with the SLE Gaussian free field coupling, also in other contexts too. And they also provide some tools for generating local sets using unions. And this is also very, 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 very useful. All right. And the reason that this is related to the SLE Gaussian free field coupling is that this is one way to construct the coupling of many SLEs with the Gaussian free field once you've constructed the coupling of one SLE, because you can take unions. So yeah, so this is what allows one to couple many SLEs with the Gaussian free field simultaneously. And all that you need to do is you need to feed into it the basic SLE Gaussian free field coupling result we did last time. Okay, and so this is one of the reasons why this turns out to be so useful. So what I'm going to do now is I'm going to state without proof a few of the results from this article by Schramm and Sheffield. And if you want to read the proofs, you can find them there. It's not very long. And then what I want to do is state, and I'm actually going to prove another result about what happens when you explore the Gaussian free field with an increasing family of local sets. So you imagine, for example, generating, kind of continuously generating one of these flow lines and trying to understand what happens with the Gaussian free field. And this is where the circle averages are going to come back in. Okay, so that's the plan, and so let me start by just telling you what these results are regarding taking unions of local sets. And unfortunately, due to time constraints, I'm not going to describe any of the locality tests because they're a little bit more technical to state. But again, if you're interested, you should definitely take a look at either their paper or Venderlin's notes, because these are also very powerful for checking that certain sets are local, which don't, from the definition, from how you would construct the set, it's not immediately obvious why they should be. But using these tools, you can give a very short, slick proof of that. All right, so before I state the first result, let me just tell you, I'm going to write a calligraphic C sub a for the function h1 in the definition of a local set. So this was the thing which is a harmonic on the complement of A. And this is consistent with the notation from Schramm and Sheffield's paper. Okay, then the first result that I want to tell you about is the following lemma. And what it says is that if A1 and A2 are local sets, and I'm going to assume that these are conditionally independent given H. Then it's true that their union is a local set for H. Okay, so if you have two Gaussian free field local sets, then you can take their union and you get something which is also a local set. So for example, in the setting of the SLE Gaussian free field coupling, you could draw one flow line, say A to 1, and then that's going to be a local set. And then you can toss in another one, A to 2, and then their union is going to be local, provided you sample them to be conditionally independent given the field. Now, in many cases, like in the SLE Gaussian free field coupling, it's the case that both of your local sets, A1 and A2, these are going to be measurable with respect to the field. And so, in this case, it doesn't really mean anything to take the conditionally independent union because they're both just deterministic functions of the underlying field to begin with. Okay, so you can take unions of local sets, but this first result doesn't tell you anything about the conditional expectation of the Gaussian free field when you condition on two local sets at once. So it doesn't tell you how.
A question.
Yes.
When you say local sets, that you are actually saying that it is a coupling of a local set and Gaussian free field.
Right. So here, that's right. And so here I'm assuming that you have a coupling. Yep.
Why don't you? It means that you don't just take this relatively this independent joining. You always can take an independent joining of two.
That's right. But
you don't. You just
so
took this independent joining here.
Right. And so the reason is that, yeah, so any given local set has sort of a coupling with the Gaussian free field. But if you have two at once, it's not clear how they're supposed to be coupled together given the Gaussian free field.
But you always can, if you have like a common factor.
Right.
Yeah. So it just means that.
That's right.
Yeah.
So if you have two local sets, you just choose the coupling
Yeah.
in which they're conditionally independent given the Gaussian free field. Right. And then just to emphasize, in many cases, like for SLE curves, they're actually just going to be deterministic functions of the Gaussian free field. And so this particular point you don't really have to even worry about. Okay. So now let me tell you about the next sort of important result in this direction. And that's that, again, if you have A1 and A2 local sets of the Gaussian free field, which are conditionally independent given H, then it's true that if I look at so I keep referring to this as the conditional expectation of the Gaussian free field given these two local sets, then this function is going to agree with the conditional expectation of the Gaussian free field given just one of the local sets. And by this I mean that if you take their difference, then this is going to go to 0 as z tends to any point x which is in a component of A1 minus A2, which is larger than a singleton. Okay, so again, the first result tells you that the conditionally independent union of two local sets is local, but it does not tell you anything about the boundary values of the Gaussian free field when you condition on both of the local sets at once. And the second result tells you that if you have your two local sets, let me draw a picture now. So let's say this is A1, and you have another local set, say A2, then what this result tells you is that you know that the boundary values of your Gaussian free field given both of the local sets is going to agree with what you would have gotten if you had just conditioned on one of them if you are at a point, say in A1, which is at which is not in A2. Okay, so it tells you what the boundary values are going to be here, but it does not tell you what's going on at these 2 points in this picture here and here. So where the two sets intersect, this result doesn't tell you, does not tell you what the conditional expectation of the height is supposed to be. Okay, so right. Okay, so these are the two results that I wanted to tell you about from this paper of Schramm and Sheffield. And now what I want to do is tell you about an interesting result that tells you how the law of the Gaussian free field evolves when you start conditioning on larger and larger families of local sets. And the relevance of this result is that it allows you to sort of deal with the problem that you have when you condition on two local sets at once, and you don't know a priori what the conditional expectation is doing at these kinds of intersection points. And so here's the statement. So it says that if you have a domain in the complex plane, which is bounded, and for simplicity, I'm going to assume that it's simply connected. And then I'm going to assume that z sub t, for t greater than or equal to 0, this is an increasing family of closed sets in D, and I'm going to assume that they satisfy two properties. So number one, I'm going to assume that the complement of z sub t, this is going to be simply connected for all t. And number two, I'm going to assume that if I take my sets z and I stop them at any stopping time tau, then I get a local set. So z sub tau is a local set for the Gaussian free field for any value, for any stopping time tau. And this is a stopping time for the filtration generated by z. So this is a stopping time tau for z, for this process z. Okay. Okay, and then I'm going to fix a point in my domain, D, and I'm going to make one more hypothesis, and that's that I'm going to suppose that the conformal radius of my point inside of the domain, this is going to be is continuous. Okay, so my set's not going to have any jumps. Then the statement is that if you look at the conditional expectation of the Gaussian free field, given your local set at time t, evaluated at z, and the difference between that and the same thing but at time 0. So this is now a stochastic process in, it varies in t. Then the statement is that this this evolves as a standard Brownian motion provided time is parameterized. So if you reparameterize time so that the log of the conformal radius of z in d minus the log of the conformal radius of z in d minus the local set up to time t is just equal to t. Okay, then this conditional expectation just evolves as a Brownian motion. So let me draw a little picture now to explain this. So all that's going on here is you have your domain, like this square here, and you imagine that you fix a point here, like z. Then what the statement says is that if you start growing some local sets towards z, so you're sort of exploring your Gaussian free field, and you're conditioning on sets which are getting bigger and bigger. These are the z's. Then if you parameterize time appropriately, it's always going to be true that the conditional expectation of the Gaussian free field here is going to evolve like a Brownian motion. Okay, so you can write down exactly what the law is. And we've actually already done an example of this in disguise. So let me just quickly remind you of that. So the example that we did of this earlier is just if you take your domain D, let's say it's just the unit disk, and you take your set Z sub t just to be the deterministic set, which is the complement of the ball of radius e to the minus t in Z, or sorry, in the disk, then with this particular choice, the conditional expectation of the Gaussian free field, given its values on this set at the point 0, let me draw a picture over here. So here's the unit disk, and we're looking at the Gaussian free field given its values in the complement of the ball of radius e to the minus t. Then this conditional expectation is going to be exactly the same thing as the circle average on the ball on the boundary of this ball of radius e to the minus t. And we showed earlier that this evolves as a standard Brownian motion when you vary t. And so this result, this is just a generalization of this to any family of local sets which are continuously increasing in this way. And one of the reasons that this is extremely useful is that this tells you that, in particular, this function that you get is continuous in time. So somehow, if you have a family of sets which are local for the Gaussian free field and they're increasing in a continuous way, then you can't have any jumps in the conditional expectation.
I mean, just a question: when you have a Brownian motion, you don't have immediately that is continuous.
Right. So yeah. So to make this precise, I mean, you have a modification which is continuous in t, and actually you can make this jointly continuous in both t and z. Yep.
At the point z does not belong to the set z of t.
Yeah, so I'm assuming, this result holds up until the first time that the log of the conformal radius, just the conformal radius goes to 0. So up until that time. Yeah, and again, so this is very useful because this tells you that this process after passing to a modification just can't have jumps. And what I want to do in the last 15 minutes or so is just explain the proof of this, because this is going to combine a number of, well, just a few of the things that we've done so far. All right, so yeah, the first step is it's kind of a trivial lemma, but let me state it. So what the lemma says is that if you have random variables, x and y, which are independent, and you know that y is a normal random variable with mean, say, mu of y, and variance sigma of y squared, and you know that that their sum, z, just x plus y, if this is a normal random variable with mean mu of z and variance sigma of z squared, then this implies that x is a normal random variable with mean mu of x, which is given by the difference of the means of z and y, and variance sigma of x squared, which is equal to the difference of the variances of z and y. Okay, so this is kind of a basic probability exercise, but it's going to be very useful in the proof that I'm going to give in just a moment. And so one way to prove this is that you can just use characteristic functions. So I won't go through the details of this. Okay, so that's the first fact. And now we're going to use this to prove what's kind of the main input into the proof of this this statement. Okay, so all right. So now here's the next. This is kind of the main lemma that really gives it to you, actually. And here's what it says. So I'm going to assume that A is a local set for my Gaussian free field. And I'm going to assume that the conformal radius of z in the complement of A, this is almost surely positive and constant. Okay, so you have your domain and some point z, and you have this local set such that regardless of its realization, the conformal radius of z is always going to be the same. So kind of implicitly in this, I'm assuming that D complement of A and D is simply connected, so that the conformal radius makes sense. Then the statement is that the conditional expectation of the Gaussian free field given A, evaluated at z, this is a normal random variable with mean 0 and variance given by the log of the conformal radius of z and d minus the log of the conformal radius of z and d minus a. Okay, so this gives you the exact law of the conditional expectation of the Gaussian free field once once you condition on A, evaluated at Z. It just has this very simple form. And if you think about it, once you have this, this will exactly give you this statement over here, because this tells you that this conditional expectation, when you have larger and larger z's, is going to have exactly the same finite dimensional distributions as a standard Brownian motion. So this is really the key thing. And right, and this statement, this is just a generalization. It's actually just going to follow from what it's supposed to be generalizing. It's a generalization of the fact that this is something that we did earlier, that if you do the circle average, if you look at the difference of the circle average of the Gaussian free field about two circles, so one of which is of radius e to the minus t minus s, so this is a smaller circle, and look at the difference between this and the circle average about the circle of radius e to the minus t, then this is a normal random variable with mean 0 and variance s. Okay, so this is kind of a generalization of this fact, and actually this is what's going to tell us that this is true. All right, let me leave the statement of the proposition there, and I'm going to write the proof of the lemma that I want to show over this trivial lemma here. Actually, no, I'm going to keep the trivial lemma, and I'm going to write the proof on this board. All right, so here's the idea. So let me remind you one more time that if I have epsilon positive and z and d such that the ball of radius epsilon centered at z is contained in my domain. So if this is true, then the average of the Gaussian free field on the circle of radius epsilon centered at z, this is going to be a normal random variable with mean 0 and variance minus log epsilon plus the log of the conformal radius of z and d. Okay, so this is the basic result. All right. So now what I want to do is I want to pick an epsilon positive so that the ball of radius epsilon centered at z is disjoint from A almost surely. And you can do this because we assumed that the conformal radius of z in the complement of A is positive and almost surely constant. You can always find a ball which is disjoint from A. All right, so now, so what do we know? We know that that if you take the Gaussian free field, H, and you subtract C of A, then this is going to be a Gaussian free field on the complement of A, because that's just the definition of locality. And if I take this Gaussian free field and I average it on the ball of radius epsilon centered at z, this is going to be by this fact I just explained here, this is going to be a normal random variable with mean 0 and variance given by the log of its conformal radius inside of this domain. So its variance is minus log epsilon plus the log of the conformal radius of z in d minus a. Okay, but this is also, this function here, I can write as h epsilon of z minus ca of z. And the reason I can write it this way is that this is a harmonic function, so if I average it on the boundary of a ball of radius epsilon, I just get its value at the center. So I just get that. Okay, so I've determined the law of this quantity here. But now what I can do is I can write h epsilon of z. This is the same thing as ca of z plus h epsilon of z minus ca of z. And in my trivial lemma, this is going to play the role of y. This is playing the role of z. And this is going to play the role of x. And again, since I know that y is normal with mean 0 and variance minus log epsilon plus the log of the conformal radius of z in the complement of a, and this guy I know is a normal random variable with mean 0 and variance given by minus log epsilon plus the log of the conformal radius of z and d, then the trivial lemma from before tells us that x is a normal random variable with mean 0 and variance given by the difference of these two variances. And so I'm just going to get the log of the conformal radius of z and d minus the log of the conformal radius of z in d minus a. And that proves this fact. Right, and so once you have this, this tells you what happens, what the law of an increment of this guy is when you vary t. And once you know that the law of an increment is the same as is for Brownian motion, then you can always find a modification of this so that this is just a standard Brownian motion. And again, this result, the way that it's used, or one of the ways that it's used in practice, is that it allows one to sort of deal with this problem here, where when you condition on two local sets, you don't really have a handle a priori on what happens when they intersect. Okay? But if you're in the SLE setting, so the problem that arises when you do SLEs is that you have your, you have one SLE. That's a local set, so that's fine. And then you start going another one. What can happen is that this guy can start to hit this guy and bounce off of it like that. And what you want to be able to do is calculate the conditional law of one given another. And in order to do that, you really need a good handle on what the boundary data is when you start conditioning on both paths. But in principle, this result here it just does not say anything about what's happening at these intersection points. In principle, you could have some bad behavior whenever they start to hit. But the way that you get around this is that the result we just went through tells you that somehow the when you condition on the two paths, as you kind of grow one of them and they hit, you can't have any jumps in the conditional expectation of the height, and therefore kind of nothing bad can be happening at these intersection points. And it's also extremely useful for other things in practice when you work with Gaussian free field local sets. So I think that I'm out of time, so I'm going to stop there. So does anybody have any questions? Yeah.
Yeah, when you apply the simple lemma, you need to have independence. Is independence clear?
So the reason that they're going to be independent is that if I condition on, so what I know is that if I condition on C of A, then the law of this is going to be a Gaussian random variable with this mean and, so I mean 0 and this variance here. But then the important thing was that I assumed that this quantity is non-random. So this is a deterministic, and that's why you know that they're actually independent. Does anybody have any other questions? Okay, so I'll stop there then.